So the way to read this probability is the probability of the one speed is between these two numbers. The reason we care about this is that your turbine will have a cut-in speed, will have a cut-out speed, right? So often we want to understand is, okay, how long, what are the probabilities your turbine is actually off? Right? Where your turbine is actually operating, generating power. So very, very often we compute this kind of thing. Right, so we're very interested in this probability as well. Okay, so for this kind of probability, basically is you sum up. So let's say, let's have an example. Basically, let's say W1 is 0, W2 is 1/2, W3 is 1. It's closer. Okay, so let's say we have this kind of possible values for this. And let's say that, so I'm going to assign some random probability to this. So I'm going to pick 0.1, 0.5, 0.1, 0.1. Let's say these are my probabilities associated with values. And let's say we have so here we can ask the question, what is the probability between this happens? Right? We can ask this probability. So what is the probability of W being between these numbers? Okay. So what is the so again interpret in the context of this class, if you have a turbine, this is your cutoff, this is your cut-in speed, this is your cut-out speed. What is the fraction of time you're on? What is the fraction of time you're within this speed, meaning you're actually operational? Okay. So to compute this is pretty simple. Okay? You look at, does this satisfy the inequality? Right? So each one of the values satisfy inequality. You sum up all the probabilities for the values that satisfy this inequality. Okay? So here you sum up 0.5 plus 0.1 plus 0.1, this is 0.7. Okay? So this is the probability of your value landing in this range. Okay? So this is not in the range. This is not in the range. Everything else is. Sum of the probability, get to this value. Okay? So these are, so these two things, one is computing sort of the probability over an interval. Another is computing the function of a random variable, as well we'll do a lot. Yeah.
You're basically like instead of having a video
right.
discrete by fitting it. So
yeah.
Like just is this working in discrete for the second stage of like making it simpler, but like is there a specific way to fit these things? Like is it like greater than 0, less than 1/2?
Oh yeah, so you actually practice how to bin this, is you bin them as funny as possible. Right, that's sort of how you bin. You bin them as funny as possible. So here, yeah, so here for us to have a workable table, you don't bin that funny. But in practice, so we'll get to this a bit later. There's many ways to do this estimation. Okay? In practice, often is if you directly want to compute this probability, you just compute this. You don't even bother with the bin. Because you have a lower bound, you have a upper bound. You look at all the value recorded, you count the fraction, that's within the step. That will give you this probability. You don't need to create a distribution. Right? So in practice, if you after this question, just compute this question. If you have some other question, just compute the other question. And not have a distribution first. You don't necessarily need to construct a distribution. Okay, so that's what typically what happens in practice actually. Okay, so we need a distribution because we need to talk about this kind of thing, we need to be computed. In practice, nowadays is you record the raw data, in real number, right? You measure a finite percentage real number, just try to answer this type of question directly from the data without constructing a distribution first. Okay, any other questions for this? So these will be the typical calculations, right? So we'll do a lot, but it'll be this will be the calculations we do. Okay, so probability again, right? So again, the important thing is to remember this kind of thing has to come out again a number between 0 and 1. With whatever probability you're computing, it should be a positive number between 0 and 1. Okay. So that's a probability. Right, so this is probability. Again, last time we said is, as just as the question answers, finding a distribution is actually very hard. In fact, finding a good distribution is difficult. Hard, and even if you have a sort of discrete distribution, it's hard to communicate that to people. It's very hard to communicate the distribution to people, and it's hard to make decisions based on a table of numbers. That's the kind of thing to do. So we have statistics. Right? So last time we said these are basically just sort of, you can think of single number summaries. Okay? So these are you compute the distribution, think of it as a big table of numbers. A statistic is a single number you can compute from this distribution that will tell you something interesting. Okay? That will tell you something interesting. So the most basic one is the mean. Or average, or expected value. Okay, so they have exactly the same definition. So some textbooks will call it mean, some people call it average, some call it expected value. In probability, if you actually take a probability class, you'll see this term being used, expected value. When people don't typically want to use this, it's because you tell engineers this is expected value, they think that's a value. Okay, this is a sort of communication issue. So in wind, what typically you see this average, not expected value. Right? Because in wind, what happens a lot for wind power is either you have no power or you saturate the turbine. You operate at your max power. Okay, so you tell people this is your expected value, it's actually a value of something that you never operate. This creates a lot of confusion for people in the field. So we tend not to use this word, although this is a standard terminology in the field of probability. So you do communications, for example, they just say this is the expected value of this random variable or something. Right? For us, we don't say that because the chance of you actually getting this value is very low. And then people think they should get this value all the time. Right? So there's similarly, to a lot of scientific communication, right? You do polling or something, you never hit the average, you never hit the expected value. So we don't tend to call this, right? So for us, we'll call it the mean or the average, the terminology for people. Okay. So this has so the notation for a mean, the notation is E of something. This E again comes from the expected value notation. So this notation is standard, it's just E of. The notation is the expected value of this random variable. To compute this is a direct averaging for us. Okay, so the averaging goes, you look at all the values, you take the value itself, you weigh it by the probability the value can take. By the probability that you're taking that value. So this is a weighted average, right? Weighted by the probability. And you compute some number, that'll give you the mean. So this is the most common statistic you see. Right? So again, it takes the entire distribution, translate into a single number. And we can communicate the single number much more efficiently, much more efficiently. Okay, so this is often we'll compute this number, right? So just doing this sum. Okay, so again, this is so you have to use a value weighted by the probability. We can also, for us, we'll do this calculation a lot, right? This has to do with this has to do with the power, right? It has to do with wind power. So this is okay, so this is the same thing. Just you raise this number to the cube. So this is expected wind speed. This is expected wind power that we have, proportional to expected wind power that we have. Okay. All right, so this is the mean or expected value or average. Again, you see all this terminology that comes up all the time. So the next most common thing we'll care about is something called the standard deviation or variance. Okay, so variance is another statistics that's very often used. Okay, so you look at whenever you do an exam on Canvas, score comes out, you get a standard deviation. You get all these measures. So this again tells you how spread out this thing is. Because the problem with the mean is it cannot distinguish between these two different situations. For example, again, let's if we have this kind of situation, equally likely, or W1 is minus 1/2, W2 is 0, W3 is minus 1/2, all the p's are 1/3. These two will have the same mean, they'll have the exact same mean, but there are different distributions, some difference in the distribution. So variance is a way to take off the difference. So variance tries to measure how far away you are from the mean for each of them. Right? So this is the equation for this. This has a name called sigma squared. This is again a very standard name. It's almost everywhere. Variance will be sigma squared. This is some summing over the probability times the value minus the mean square. Okay, so what this says is you take a value, you subtract the mean away from it, you square this. And then what you look at is, well, this is how far away you're from the mean. This is how far away from it. So this is called a variance. A bigger variance means your distribution is more spread out. A smaller variance is more compact distribution. Okay. So again, for wind, typically we want a big variance. We talk about speed, right? So higher speed gets cubed, generate power. Okay, so if you compare to one side with the same mean, the one with the higher variance typically provides more power for us. Okay, so all these are, again, communicate something about this random variable without showing people the whole distribution, the entire distribution. So you can talk to the variance of W, you can talk to the variance directly on W cubed, all these things we can talk about. Okay, so the standard deviation, so just by definition, this number. Okay. So from this number is you have a unit. That's you have a unit that's squared. So the standard deviation brings it to the same unit. All right, any questions on these? Okay, so yeah, so you do for this section of class, we'll sort of continue to do this type of calculation. Okay, given the big table numbers, find the mean, find this, find all that. Okay, so this is what we care about again in statistics. And most times we'll go from a distribution to a statistics. Right? Distribution is what you can do by collecting data. And the statistics, what you compute to sort of meaningfully for yourself to understand what the data is, and then to communicate to people what this is. Okay, so that's the idea of this. Right, so let's do some examples, right? So let's say we want to find the mean and variance. One wind farm has 3 possible speeds with these probabilities. One wind farm has 4 possible speeds with these probabilities. Compute mean and variance of these. Okay, so this is just strictly plugging into the equation. I try to compute this. So let's say for the first wind farm, we have the expectation of this W farm 1. This is 0.3 times 0 plus 0.5 times 5 times 10. Right? So this is a average calculation. We get 4.5 meters per second. Okay. Then we can compute the standard deviation. So this is sigma 1 squared. 0.3 times 0 minus 4.5 squared. Right? Plus 0.5, 5 minus 4.5 squared, plus 0.2, 10 minus 4.5 squared. Okay. So again, the important thing is don't ignore 0, the standard deviation calculation. Right? It's every number subtracted by the mean square. Okay, so the first one, this 0, multiplied by anything 0. But when you compute standard deviation, you have to take care of every possible value. Terms here. So this tells us this is 12.25. And this thing has a weird unit now. The unit for this is per meter per second square. So that's just a unit for a variance. So for standard deviation, we have this is to get the unit to be the same. This is 3.5 meters per second. Okay, so this has a mean of 4.5 meters per second with a spread of 3.5. Right, so this is one example. We can repeat it. Same thing for farm 2. We have a mean of 4.4 meters per second, sigma 2 of 3.14. Right. Okay, so this is directly basically plug into the formula and compute all this numbers. So not much going on there. The sort of basics of mean and variance calculations. So this is another reason why we use discrete values. You can actually do this calculation. We use continuous random variables, and the integral becomes hard to do. And so these things actually, you can program a computer to do all this calculation. Right? Any questions about the calculations? Okay, good. So next we'll talk about how do we get the distribution. Right, so if you look at one side, there's 0 chance you will have a distribution. Okay? There's 0 chance you will have a distribution somebody gives to you. Right, you say, okay, if you look at the wind outside, on the quad, what is distribution for wind? No. Okay, so normally what you have to do is you have to look at something called empirical probability. Right, you basically have to measure what the distribution is. Okay. So this is sort of built on measurements. This is from measurements. So let's say think of hourly measurements to have a concrete thing in mind. We don't have to do hourly, but here we'll do hourly. So let's say at hour t, we'll measure WT. Okay, let's say this is in meter per second. We take some measurement, this is a meter per second. Then after an hour's we have sort of n measurements. Okay, so this builds up a distribution. Okay, so this builds a distribution. I have n values. I can, for example, compute the mean. I can compute the variance. I can compute the probability of the measurements are between two values and so on. Okay, so this by itself now is good enough to compute a lot of things we want to compute. Right? I just took all the measurements I want. Okay? So if you took finally, if you took every minute, you just have more numbers to deal with. Okay? So from these, we can directly compute the expectation, the variance, all those kind of things. But typically, we don't stop here. We will do a binning, because often as you end up with a lot of measurements, and visually it's hard to show people what these measurements are. So you want a visual representation, and you want sort of bin measurements as close together to each other. This way you can build a curve. You can actually look at it. If you don't do that, there's no curve. It's sort of flat line. Right? Everything happened once. Every value happened exactly once. It's very hard to tell, if some value is more likely than others. But when we do computations, you just stop here. We'll do a visual representation. We'll do some binning. Binning is merely a way for us to look at it, and for us to visually look at it, and for it to make sense for us. That is good and is very important, actually, to have something you can look at for this kind of probability. Okay? We just blindly do calculations. A lot of times things go wrong. So we can bin the measurements. You can assign it to however you want to assign it. So let's say we can say 9.5 to 10 gets us to 10.5, gets assigned to 10. Right? So we can bin this. We can now bin this measurements. So we have k bins with n1 nk samples in each. Right? So each of them will have some samples in them. And then now we can, instead of taking all the measurements, we can just do it with k measurements here, and looking at the value each bin is assigned to. And so here what we have is, of course, when you add this up, you just get the total number of measurements back. Okay. So this is our procedure. And for the reason for doing this procedure is to show something like this. So the reason you bin this is you want to build a visual curve like this. It's more likely to have speed here. It's less likely to have speed here, and the tail is quite long. So these you can see by sort of visual representation. It's hard to get a number to exactly describe how long a tail is. Right? So here I want to look at. If you don't bin this, what happens is this whole thing is flat. There's a very long line that's flat, because every value happens once. Right? So we need to bin it to build this kind of histogram to look at. Again, the question, when you compute anything, the actual way you compute it is directly from each sample you have collected. This is just a way for us to look at it. Right? So the idea of empirical probability, then this is quite simple. This is we have k bins, n1 to nk. These are the frequency. And then we have pi. So that's the way we'll assign probability. As we just look at how much samples we have in each of the bins. And then after that, divide by the total number n, we can assign probability. Okay, so after assigning this kind of probability, again, each number here will be positive. They'll sum up to 1 by definition. So this gives us good probability distribution. And then from this probability distribution, we can do all the calculation I've done before. Okay? So that's normally how we get this kind of numbers. right? So again, there's one speed. We can compute the one speed, right? So when we do this kind of computations, we'll treat it as if the empirical distribution is the probability distribution we have. We'll collect all the data, we'll build an empirical distribution. Let's just compute the average based on empirical distribution. So this is average speed. We have seen this equation before. So again, you sum it. So for this, for the next homework, you start doing this kind of calculations. And then because again, the nice thing is we can, you have computers now, so do some programming where there'll be a sort of a large number, okay, will be a table of things. You can download the data and compute all this kind of thing. Okay. Again, so I assume you have enough programming access to compute something like this. Compute this kind of quantity. Okay, so this average one speed. We have the average when the variance and standard deviation. Again, same thing as before. Variance is value minus average squared. Standard deviation is the square root of that. Right. So okay. So those are standard. Now this is a interesting question. This is an interesting question. So the question is the following, right? So if you look at one speed again, there is some true underlying distribution, right? One speed is generated by some probability distribution. Let's think of that way. What we don't know what the distribution is, right? We don't know what that distribution is. So what we can do is there's some distribution. Okay, we don't know, right? This is by nature. Nature has some distribution. We have no idea what this distribution is. So what can we do? Well, we can pull n samples. What we can do is we can go and measure this thing, many times. After measuring this thing many times, we can collect. We have something like an I and WI. So this is frequency. This is value. Right? So we can do this kind of empirical calculation. We can do this empirical calculation. So we can compute this number. Okay, we can build this number. So the question is, there is distribution. So this distribution has an average. There is a true average. We don't know this. What I can do is I can sample this n times and compute this number, right? So I can compute this average. How are they related? Okay, so that's a question that you're asking probability is. There are some in statistics, actually. There are some true things here. Now I don't know the true value. If I knew the true value, I'll be done. I don't know in practice, you never know the true value. So I can build an estimate. This is called estimate because it's from your sampling, you build estimate. How are they related? Any intuition on the relationship between the two? Is this a good estimate of this thing? Or when is this sort of W hat a good estimate of this? Right, so the hope is as n gets very, very large, this estimate will eventually go to the true value. Okay, so that's a hope. And that's an assumption that we make in the field. So as large, this sort of approximate the true value. Okay, so we'll think of this as being an approximation as a true value. Okay. The issue with this statement is, one, this doesn't always happen. There are situations, you can construct situations where as n gets large, this is not a good estimate. Okay, so there's very often in practice, so if this happens, this is called unbiased estimate. It's very often in practice you don't have an unbiased estimate. Every estimator you have is biased. Like there's no way to estimate the mean. Another problem is what does large mean? So this is often a problem we have. Is how many data points do I have to get to be large, to get this into a large regime? So for wind, this is typically constrained by the fact that you take as much measurement as you can. Right? Just take as many as you can and say, well, this is the best I can do. This is sort of the best thing I can do. In other settings, in statistics, this gets much more complicated. For example, think of the COVID vaccine trial, right? You need to take some number of people. You have to observe them for a while to see what the efficacy of the vaccine is. How large is large for this kind of thing. That gets very complicated for us. So for us, we'll pretend this number is actually this number. Okay, we'll just pretend this is true. To make this happen in practice actually takes some effort. So let's say you try to find a site that you want to build a wind turbine. You try to get some understanding of what the average speed is, what is all that. Right? You have some finite budget of measurement, so you cannot measure every hour of every day for 5 years. Right? You have some finite budget. So how will you actually go about measuring this kind of thing? So in a practical setting. Let's say you are given some money. They tell you, okay, you can go to the site and measure, let's say 1,000 times. When will you do those measurements? How will you do those measurements? The idea is what? Right. So one thinking is, okay, let me spread it out, right? So let me measure, morning, noon, night, try to capture as good a representation as I can. Right. Let me try over different seasons, right, to see, what all these are. In practice, we don't do it that way because again, we care about high wind speed much more than we care about low wind speed. Okay, so in practice, the way you measure this kind of thing, actually, when you try to develop a wind turbine is, first you do a couple measurements, figure out when typically high wind and low wind is. They disregard the low wind possibilities, you don't care. Okay, I don't need a very accurate estimate of low speed wind. I don't generate power that way. You figure out what are the possible high speed times, then you measure those very accurately. Take a lot of measurements there. So doing this in practice, there's a lot of art to this. Okay? So for us, with an estimate, the assumption is always, our estimates are very good. In practice, that may not be the case. For this class, we just have a good estimate. We always have a good estimate. So this estimator is estimating something called a mean as a single variable estimate, single value estimate, right? So again, we often want to estimate probability. So we care about the probability again as, so let's say cut in less than cut out. So in wind, we really want to know this kind of probability. We really want to know this kind of probability. This is the average amount of time your wind turbine is actually operating. This is probably no. And the way to do this estimate is again fairly simple. You basically look at all your data and see when this is true. Okay, so you have, right? So let's say we have measurements. All these measurements, and this is roughly the summation of the indicator function right? So this is sort of 0, 1 function you have. So this is the indicator. This just means it takes a value of 1 if the condition is true, takes a value of 0 if the condition is not true. That's how you program this kind of thing. So this is a 1 if So the condition is true, 0 is false. Okay, so this is the way to estimate this type of probability. So again, if you build wind or solar or this kind of renewable things, you do this a lot. That's what we do. So if you allow development people, right, when they try to develop a site, they first go in and measure this kind of speed. And from this data, trying to figure out, more refined, what is the top speed, what is sort of the likelihood you operate at close to the, for example, the cutoff speed and all that. Okay, any questions? Okay, all right, good. So yeah, so these are the estimates we can do. So now is probably a good time to take a break. Then we'll go to something, we'll try to develop something called a continuous probability density function. So the way the discrete thing is good, we can, for a computer, it's very nice for a computer to do all these calculations. For us, again, it's not so nice because we don't want to always think about things in so many, a big table of numbers. Okay, so let's come back at 9:30 when we'll look at continuous probabilities. What if the numbers are continuous values? Okay, all right, so okay, so to get to the continuous value, so the reason again we want to get to a continuous value is for a probability, what we can do, right? What we can do is we can compute this kind of statistics. We can estimate the statistics. We can, given the value, we can estimate the mean, we can estimate standard deviation, and so on. For a discrete distribution, it's very hard to go backwards. For example, if I say I told you the statistics, now I want the entire distribution. For a discrete distribution, that's actually not easy to do. For continuous value things, it's more natural to think about this in continuous fashion. For example, the Gaussian distribution. The reason Gaussian is nice is because it's completely described by its mean and standard deviation. That's it for Gaussian. Right? So want to build up to that. So the way we're going to do that is to go through something called a CDF. Because this thing is defined for both continuous and discrete. So CDF is the following probability interval. That says, give me any interval, I can compute the probability my random variable lies in this interval. Okay, so you pick any interval here, you sum up the probability here. So this is called a cumulative distribution function. This is the name, or cumulative means you're summing up. So this function will always take a value between 0 and 1. There's some value between 0 and 1. You can, depending on where interval is, you can sum up everything. That's 1. If you sum up, you're here in the middle, that's 0. So a cumulative distribution function is a number between 0 and 1, describing the probability of what's going on in an interval. This is what we have. This is actually the central object you study in probability theory. So again, you take the math probability class, you'll start out with this. The nice thing about this function is, so in probability, the question people ask is, okay, you take a random number between 0 and 1. What is the probability of selecting, let's say, a rational number? What is the probability of selecting an irrational number? Right? That is not a meaningful statement. Okay, we don't talk about the probability of selecting a rational number, right? So we don't want to talk about this kind of thing. That's weird. There's an infinite number of them. What does it mean? But what you end up describing is you always want to work with this interval. The interval is nuts. We can talk about the probability of something happening over an interval. This saves you from answering, again, randomly pick a number, right? What is, you randomly go through a natural numbers. What is the probability, taking some subset of? So rational number is a good, good example. We don't want to talk about it. So we talk about things happening in this interval. This is always well defined. You always define this function between 0 and 1. So once we define that function, we can do a lot of things to that function now. So from the CDF, we can define the probability density function. What this probability density function means is, now what happens when I think of the interval happening in smaller and smaller sizes? Okay, so CDF, we have all these intervals. What if I squeeze the interval closer and closer together? What do I get? Well, there you don't get a probability anymore, you get a density. And this is a continuous distribution. This is a continuous distribution. And the reason we use this is very easy. You can use this sort of, it's very easy to parameterize this distribution. Again, Gaussian, very easy to parameterize. Not so easy to parameterize a discrete distribution. So the way to get this function is to take the following limit. Let's take the following limit. Let's think of, so this has a notation of f, small f, as thought of the density function. Typically, we'll use a small f, because p is taken by probability. So we don't use p. So we use f for density functions. Has this interpretation is you take a limit. So what do we take a limit of? We start looking at the probability of the following region. We look at some wind speed. Okay, so what this says is I have some random variable w, this wind speed. I look at the probability of this wind speed between these two limits. So it's little w plus dw. So I want to know this between these two limits. Now I can squeeze this limit, basically makes this dw go to 0 and compute this limit. This limit most of the times will exist. Okay, this thing will exist. This limit will exist, and this is called the density function. Okay, so this is some function. So for each small w, you can put in. For each small w, you get a number out of this limit, and this will describe a density to us, right? This is very close to the small w. What is the likelihood of getting this value? So this is by definition called the PDF. This is just a definition. So if this limit exists, for us, this limit will always exist. This limit always exists. And this is the probability density function. So this is the derivative. Okay, so what happens is you're basically differentiating the probability. You take a probability, you do a derivative. By definition, this is a derivative. So this gives us a function that is easy to work with most of the time. This is an easy function to work with. Okay. And this function has several properties. This function has several properties, right? So the property to note about this function is one, this is always right, larger or equal to 0. Because this number is always right bigger than 0 or no. This non-negative number. We take a limit of a sequence of non-negative numbers. This is some non-negative. So this is always a some non-negative number. And then the thing that happens is the integral from -infinity to infinity. This is 1. Take a density. You sum up all the little pieces of all the probabilities. This integral, after doing this integral, they have to be 1. So I'm summing up all the densities. But this greater than 1 is okay. It's definitely okay for the value of this density function to be larger than 1. This is typical. This is fine. As long as this integral comes out to be 1, then you're okay. Then you're okay. The density can be larger than 1. The reason the density can be larger than 1 is, again, you're talking about derivative. You're talking about derivative of probability. So if things are very concentrated in one region, then this rate of change can be larger than 1. So this is okay. It's okay for a density function to be larger than 1. As long as the integral is larger than 1, then it's okay. Okay, so what's one as a, right? So as the basic example, you can think of, for example, let's say if one only has one speed. Okay, let's say one only has one speed, let's say 10 meters per second. That's the only speed it can ever possibly have. So what does the, what, okay, so let's say, so this is with probability 1. Okay, so this is for sure, it always have one speed. Then if you look at the CDF, what this looks like is, this will be 10 meters per second. There's 0 chance this thing is less than 10 meters per second. There is 100% chance this thing is when there's right. So there's 0 chance that one will be less than 10. There will be 100% chance one will be less than any value that's greater than 10 meters per second. Okay, so your cumulative density function jumps at 10. Because this is the only thing that can happen, this can have a jump. If you differentiate this step function, what do you get? You get a delta, right? You get a delta function here. And delta function is definitely larger than 1. Okay, so it's definitely okay for this to be larger than 1. It just depends on how sharp this jumps are. Okay, so this is definitely fine. Being larger than 1 is completely fine. Okay, so this is, so the most extreme example is now you have a delta function. So normally we don't have this kind of thing, but again, this allows us to talk about this type of function. Okay, so this will satisfy the integral of a delta function is 1. If you integrate across it, is everywhere is non-negative, and at the particular point is larger than 1. So this is completely fine. Okay, and now this is good because a lot of operations become easier, right? So we can think of this probability again. If you have histograms, you're basically fitting this PDF on the histogram. You're fitting this PDF on the histogram, you normalize the area to 1, and that's your density function. So again, for this class, you will not be asked to fit a density function. That's too hard to fit. We'll give you some density function. But the nice thing is we can now work with integrals. Okay, we can now work with integrals. And integrals we can do by hand. We don't need a computer to look at a big table and sum up things for us. Okay. So for example, the probability. Now this becomes, you just integrate the density between these two limits. Okay, so this becomes a very nice thing to do. If you know the function, we can often do the integral by ourselves. We can often do this integral. Okay, so if you build up f, so pictorially, this is, if you have some distribution that's like this is A, this is B, this will be the area under the curve between A and B. So this property of the density function. And now we're going to study a sort of different classes of density function. So the simplest class we can have is called a uniform distribution. It's called uniform distribution. This is actually not a terrible distribution for one. This is not a horrible distribution for one. What uniform distribution says is the following. This is normally uniform distribution is written as sort of between A and B. So what this looks like is this is A, this is B. So it's 0 outside of this region. And the density function is a flat line between the two regions with a value of 1 over B minus A. Okay, so this is what the density function looks like. So from this, you can compute the average. The average will be B minus A over 2. B minus over 2 and all those kind of things. This is the average you can compute. Okay, so here the value of this function, this is w equals to 1 over b minus a, if w is in this range, 0 otherwise. And now we get to use integrals instead of sums. So for integral, for average speed, w times by density, integrate this thing out. Variance, this thing times w, integrate this thing out. Standard deviation, right, take the square root of this thing. Any questions about PDF? Okay, so these are by definition what we will do. Right? So if you get some random PDF, you ask to find the mean or the average, do that integral, compute that integral. Okay? And every PDF you get in this class will be, you can do it. You can do that integral. And the whole, a lot of times the reason we want to talk about it is now we can use several classes of functions to describe one speed. Okay, these are parameterized by some sort of statistics. We can use them to describe one speed. So for example, you have a normal distribution, a Gaussian distribution. If you know the mean and variance, you know entire PDF. Rayleigh is something else, Weibull is something else. Okay. And each, different people have their own beliefs on which one is the most closest to reality to describe one. So look at each one. Again, with normal being the most useful for us. So normal will be the most useful for us. And the normal distribution is very, very nice because it's entirely defined by two parameters. Two independent parameters. That's mu mean and sigma square the variance. Okay. So these being the things we can measure the easiest, and this is often thought as the most important statistics, the mean and variance. So you can ask a question, what distribution is completely determined by these two numbers independently? Okay, you want some distribution where you can plug those two numbers in independently and makes sense, and the distribution makes sense. And turns out that's your Gaussian distribution or the normal distribution. Okay, so this is our normal distribution. This is the thing that, actually, let me be more standard here. So I'm going to use the average value. Okay. So this is your normal distribution. You can look up this distribution anywhere. This is the most well-studied distribution in probability. For good reason, this is sort of exactly how you think of probability shows. You centered around the mean. Mean is your most likely value. You spread out by the standard deviation, which is what the Gaussian thing looks like. Okay. And the good important thing is if I measure these two numbers, I can plug into this function. Now I can compute everything else. I just need two numbers to describe this thing completely by itself. This distribution shows up all over the place, right? So we all, shows up again and again. There's different reasons for this distribution to show up. There's a central limit theorem that says, everything should converge to this in some sense. This is also technically the easiest thing to work with. This is technically the source. The reason, so does anybody know why this is technically the easiest thing to work with? Why do we like to assume things are Gaussian? Without worrying about whether they're truly Gaussian or not. Okay. Right, but why mathematically is this thing easy to deal with? There's a good reason why this is easy to deal with, and it's important actually for one part.
Because the distribution is symmetrical?
No, there's many, for uniform, I can make it symmetrical, right? But this is infinitely easier to deal with than a uniform distribution. Okay, so the important thing why this is easy to deal with is, let's say you have two turbines in your farm. Okay, so this is experience. This happens quite a bit. So let me describe why Gaussians are so nice. are easy to work with. Okay. So the idea is, let's say I have a farm with 2 turbines. Okay, so I have each turbine generates, some random power W1, W2. There's some random variable associated with each turbine. That's the power they generate. And now I want to look at the total power. Okay, let's say I look at the total power. I want to look at the total power. If I know the distribution for each, the question is, when can I add the distribution? Because that's the thing you want to know. If this thing is some distribution, you recorded this. If this has some distribution, if I add, what happens to this? Okay, so this is what we want to know. And so say W1, this is a uniform distribution. W2, there's some other uniform distribution. What happens when you add them? What distribution do I have? You have something that's uniformly at random over an interval, plus something else that's uniformly at random at that interval. What do I get? Do I get another uniform distribution? No, right? I don't get uniform distribution. There's some overlap between these two. When we add them, what happens is you get this weird triangle thing. The distribution becomes this triangle. Where the focus was on convolutions. That's what happens when you convolve this thing with this thing, you got a triangle. Okay, whoever done convolutions. This you can do. What if I have 3? What happens when I add a square to this triangle? You really don't want to do that convolution. Okay, that is not an easy convolution to do. So the problem with random variable and distribution typically is you cannot add them. Okay, adding distributions does not preserve the distribution, except for Gaussian. Gaussian is the only distribution where you can add and subtract independent distributions. The form stays the same. That's the only distribution where that happens. That's actually a bit definite. You can define a Gaussian distribution that way. You can prove that you have to have that form for this to happen. And so this is hard to work with because normally a farm typically has, let's say, 10 of these. You add 10 squares, you get some very weird looking thing here. What happens is Gaussian are Gaussian. So the sort of technical term is jointly Gaussian. Then it's Gaussian. And in fact, you can directly write down the mean and variance of this Gaussian random variable from each of these. Okay, so Gaussianness is preserved under linear relationships, under linear operations. So the Gaussian distribution or normal is the only distribution right? This is the only time it happens. You can show this. So the way to show this is you can look at convolution. When does convolution preserve a functional form? You have to have e to the something. That's where the only think of a convolution, the way convolution works. You're basically asking, so convolution works as I have 2 functions, you multiply them together, integrate out one of the functions. So you're asking, when do I have a function that's an integral is of the same form as itself? Right? So that's exponential. That's the only choice you have. You have no other choice than a Gaussian. Okay? So this is the only time it happens. That's why this thing is so popular. Right? Everywhere else, I cannot add and subtract. Gaussian, I can add and subtract. Okay, I still get Gaussian. So I get a bunch of mean and a bunch of variance. I can add and subtract them. I just directly deal with the mean and variance. I don't need to do convolutions. Okay? I don't need to do Fourier transforms. I don't need to do convolutions. I don't need to do none of this stuff. I can preserve Gaussian. This makes your life infinitely easier than this. So often we'll say things are Gaussian because we want to add them or subtract them or do linear operations, regardless whether they're Gaussian. We're going to just pretend they're Gaussian and work things out that way. Okay, so this is why you see this so often. You see this so often. You see this everywhere. People make this assumption a lot of times without very good reason, because it makes follow-up calculation so much easier than anything else. Okay, so we still make a lot of assumptions about wind power being Gaussian, even though it's probably not, because we want to do operations. We want to add and subtract random variables. We want to add and subtract random variables. We want the result to be simple. Gaussian is the only thing you can do. If it's not Gaussian, for example, what happens when you multiply to random variables? Very, very hard to say what happens when you multiply to random variables. Okay, so adding subtraction, Gaussian is the only thing that works. So that's why it pops out all the time. It does have this nice looking symmetric shape, right? So again, this is e to the something. So this has a tail that drops off fairly quickly. I think for Gaussian is very concentrated around the mean. This is exponential to something squared. This will drop off very quickly at the two ends. Will be centered at the mean and some standard deviation spread around. Okay, so it has two, right? So it's by far this Gaussian outnumbers everything else combined in practice. Has two parameters, both are very, very easy to measure. You get it, I can measure it. I can do addition and subtraction, and have things together. So the interesting thing about Gaussian is, so we really, really want to use, I want to use Gaussian distribution. It's easy, I can work with it algebraically and so on. But Gaussian is very accurate. The problem is Gaussian is not very accurate models. You have this problem when you come to one power. Okay, one power is not very well described by Gaussian. For example, what happens with one power is, so one power, if you look at the time trace of power actually does not stay in the middle a lot. If you look at one power, it tends to saturate for a while. Then maybe there's no power, then sort of saturates and sort of does this kind of, one power can do this kind of stuff. The way it saturates, because here, what happens? Well, you hit the steady state operation. And so remember what happens for wind. As for a range of wind speed, you're all putting the same power. That's why you see this saturation. It tends to saturate very often. For a range of speed, it doesn't do anything. Right? You don't hit the cutting speed. It tends to be zero for a bunch of time. It doesn't spin very long in the middle. Right? It's not very likely in the middle. It's either saturates or it's zero. So in no way it looks like a Gaussian. Yeah, in no way it looks like a Gaussian. Right? So the way we're going to make use of Gaussian, the way all these things are used is, the important thing is we almost never look at this kind of distribution by itself. It's not useful to look at power this way. What we typically look at is a deviation from a forecast. Okay, so the thing we typically look at is not one power, it's not a distribution of one power. As I predict tomorrow's power, I say it's 5 megawatts. What is the spread around my prediction? What is the deviation around my prediction? That is the distribution we typically look at. Okay, we never go in without predicting a nominal value. So what we typically do is we do wind speed or wind power. And this error distribution is typically pretty close to Gaussian. Okay, so that's a nice thing about it. So normally what we think about wind is plus this kind of thing. Okay, so this is a forecast. So this is deterministic. We know the forecast is. Okay, we know what the forecast is. This is random. Okay. Right, so this is typically the way we think about a randomness in the system. Again, you think about the load the same way. You have some forecast load. What is the variation around the load? Think of solar the same way. There's some forecast solar. What is the variation? So it doesn't sort of it doesn't matter what this is. If this is not Gaussian, it's fine. It's not Gaussian. It sort of matters more what is error distribution. It matters a lot more what's error distribution. So the error distribution is, very often centered around the forecast. Right? This error should center around the forecast. The error should have zero mean. Otherwise, your forecast is not very good. Okay, so your error typically is some zero mean thing with a spread. So the error typically looks, much more Gaussian. Okay, that's what your error looks like. This is the PDF of the error. And this is closer to Gaussian. At least in first approximation. At least when you first start to look at it, looks like Gaussian, right? So it's centered around zero because you don't want to bias your error. It's weird if your error is biased one way or another. You would just subtract that off and put into the forecast. Right? If you know your error has a bias. The error typically is centered around zero mean. So you're equally likely to make an error both ways. That sort of makes sense. Symmetrical, if you do a good job, this tail should drop off fairly quickly, right? You don't want to make it very large errors. So to first approximation, this is Gaussian. And we do this calculation all the time. So a lot of research, for example, you assume the error is Gaussian, and you go from there. You do a bunch of calculations. So it's not a terrible assumption. Gaussian is not a terrible assumption. Knowing the fact that if you're talking about forecast error, not the value itself, right? Not the power itself, but the error of, but if we're talking the error value, then this is not a bad thing to look at. Okay, so that's for Gaussian. So that's what we have for Gaussian. We look at the error. So of course you can say, well, how do I get closer to this shape, right? So how do I get something that's asymmetrical around the mean? Okay, what if I want something that's asymmetrical around the mean? I want, something that's not the bell shape. This is you get to, so in this class, I just finished looking at this distribution. Sorry, my Zoom died, so let me share it again. Okay, so let's look at something called a chi-square distribution. This is called a Rayleigh distribution. This is just something else that sort of improves along Gaussian. This typically is used for positive valued random variables. So for example, people said, well, if you look at things like wind speed or wind power, these are positive numbers. Right? So these are inherently positive numbers. So I want some distribution that sort of only works for positive numbers. And I want something that's not symmetrical. I want something that's not symmetrical around its mean. So maybe you're more likely to, so especially for wind speed, you have a long tail of the possible speed. So this happens for something that's not symmetrical. There's something not symmetrical, and you get this kind of chi-square distribution. All right, so again, this is just some definition we have. There's not too much to look at. The idea is you want something that peaks relatively early and have a very long tail that dies off. So this is a good distribution for wind speed, for example. So speed tends to follow this kind of distribution. And you have some average speed, very long tail after the average speed. Okay. So this is defined for positive W. You still have this e to the something drop off. you need this mean to sit here. It's just because the thing has to integrate out to 1. Okay, so this pi over 2, this numbers are here because I want F to integrate this thing out to 1. So that's why all these constants are here. Okay, so you have to have the constants for this to make sense. Okay. So this is called a Rayleigh distribution. We can still look at the mean and the variance of this kind of distribution. So it's just an alternative to Gaussian, and it's closer match to the. This is a closer match to the one speed compared to a Gaussian. Okay. All right. So again, today I have to run a bit early for the class. So let's stop here today. Next class, we'll finish with one more distribution. And then we'll try to tie this back to the operations of 1. Okay, so what happens if your power is Gaussian? Let's say you want a storage, how do you think about that? Because storage only makes sense if things are random. Otherwise, storage doesn't, there's no use for storage. I can predict everything. Our goal will be go through this and tie this to operation of a storage device. Okay, so we'll try to get there. So let's stop here today. The next class we'll finish this probability. Then we'll go back to look at operations. Okay, thanks. I will investigate the posting averages and estimations for grade.